This is a continuation of exercise 132. In this exercise, what they do is they give you two different molecules, and they ask you if you had a population of one, and if you had a population of the other, which population, one or two, would have the higher boiling point. So we want to find out which one has the higher boiling point, and a little sort of table maybe you could use to organize your thoughts on this is this right here. So what you want to do is to think about which one is going to stick together to other molecules with more stronger forces, intermolecular forces. And we talked about what those intermolecular forces are before and how to recognize them. But the molecule at the higher boiling point will have stronger forces, stronger intermolecular forces. So for example, it would have more hydrogen bonds. And if it has that, you don't have to think about the rest of these. If they tie for that first one, then you'll go to the second one. Whichever one has more dipole-dipole interactions will have the higher boiling point. If they tie for that, then you go for the London dispersion forces. And a molecule will have more London dispersion forces, one, if it has more atoms in it, or two, if it has less branching. So this is our sort of guideline. So here we have these two molecules, and we want to know which one would have the higher boiling point. If I had a beaker full of this, would that have a higher boiling point? In other words, would it boil at a higher temperature than a beaker full of the molecule on the right? So our first question is, does one of these have more hydrogen bonds? How many hydrogen bonds does each of these have? You have a hydrogen bond if you have a nitrogen, oxygen, fluorine, or chlorine bonded to hydrogen. Notice neither of these molecules have nitrogen, oxygen, fluorine, or chlorine. And so both of these molecules have 0 hydrogen bonds. So those tie. So if that ties, we're going to go to the next one. Does one of these molecules have more dipole-dipole interactions? How do you know if you have a dipole-dipole interaction? You'd have nitrogen, oxygen, fluorine, or chlorine, but not bonded to hydrogen. Because neither of these molecules have nitrogen, oxygen, fluorine, or chlorine, both of them have 0 dipole-dipole interactions. So again, they tie. Okay, if they tie, then you go to the next one. Does one of these molecules have more London dispersion forces? And this one sort of has two parts. First, does one of the molecules have more atoms? And if you notice, on the left here you have 5 carbons, and on the right you have 6. Oops. You have 6. Each carbon comes with 2 hydrogens, so this molecule on the right has more atoms. So this has more atoms, and therefore the molecule on the right has more London dispersion forces. It has more London dispersion forces, and so a higher boiling point. So the molecule on the right, this molecule, would have a higher boiling point. And if you're just thinking about how that could happen, just trying to visualize how that higher boiling point is coming about, imagine this molecule can line up with the other one, right? It can come close to the other one, and each of those can sort of line up, and all of the carbons and all the hydrogens could have London dispersion forces. This molecule on the right could do the same thing, line up, and each of the carbons, each of the hydrogens have London dispersion forces, but you'd have more London dispersion forces, and so these would stick together better than the molecule on the left. So this would have the higher boiling point. And the reasoning you would want to write out would be the reasoning that I had written in green before. Okay, how about these? If I have a population of one of these two, which population would have a higher boiling point? So our first question is, which one has more hydrogen bonds? So let's look at this molecule on the left. How many hydrogen bonds does it have? Well, to have a hydrogen bond, first thing, you need nitrogen, oxygen, fluorine, or chlorine, which we have here. But it needs to be bonded. It needs to be bonded to hydrogen. This oxygen is bonded to carbon on both sides. So that oxygen has 0 hydrogen bonds, or I should say that oxygen, that molecule is capable of forming 0 hydrogen bonds. Okay, how about the molecule on the right? How many hydrogen bonds could it form to another molecule? First thing you need is nitrogen, oxygen, fluorine, or chlorine, and we have an oxygen right here. Next thing you need is for that to be bonded to hydrogen, and it is. So this has 1 hydrogen bond, or I should say, that's capable of forming 1 hydrogen bond to another molecule. And that's the most important thing. If you get a difference here, you don't have to go to the next step. So you would only go to this next step if that first one tied. And so this molecule on the right would have the higher boiling point. It would stick to other versions of itself, other molecules like itself, more than the molecule on the left would stick to other molecules like itself. So if you think of it in terms of charges, this oxygen is slightly negative, and this, so is this one. This hydrogen is slightly positive. It's the attraction between this oxygen and that hydrogen that forms the hydrogen bond. And that would be a stronger interaction than anything you could form between these two molecules. All right, let's try D. So here we have these two. We want to follow this thought process. So first, which one of these has more hydrogen bonds? How many hydrogen bonds could this first molecule form to other molecules? First thing you need to form to have a hydrogen bond is a nitrogen, oxygen, fluorine, or chlorine. And here you see an oxygen. Okay, but it has to be bonded to hydrogen. Is it bonded to hydrogen? It is. And so this molecule on the left is capable of forming 1 hydrogen bond. How about the molecule on the right? We have an oxygen. It's bonded to hydrogen. And so this also is capable of forming only 1 hydrogen bond. How about, okay, so those tie. If they ever tie, you go to the next one down. Which molecule is capable of forming more dipole-dipole interactions? Well, when do you have a dipole-dipole interaction? You have it when you have nitrogen, oxygen, or fluorine, or chlorine, but not bonded to hydrogen. And so on the left, we have an oxygen, and on one side, it is not bonded to hydrogen. So this molecule would be capable of forming 1 dipole-dipole interaction. How about the molecule on the right? Again, we have the oxygen, nitrogen, oxygen, fluorine, chlorine, and we see that it also is bonded to an atom other than hydrogen. So it also has 1 dipole-dipole interaction. And so again, they tie. If they ever tie, go to the next one down. So here we're looking for which one of these is capable of forming more London dispersion forces. So first let's look, does one of these have more atoms than the other? On the left we have 1, 2, 3, 4 carbons and an oxygen. On the right we have 1, 2, 3, 4 carbons and an oxygen. And if you count them all up, you'd see that the number of hydrogens is the same too. So we have the same number, the same number of atoms, so that ties, and so we'll go to this last thing, the branching. On the left, do you see how this looks sort of like a straight chain, whereas on the right, you've got that center atom with branches coming off of it? And so this molecule on the left has less branching, and because it has less branching, it will have a higher boiling point. You'll need more energy, more heat to boil a beaker full of this molecule than you would need to boil a beaker full of this molecule. Because the molecules will be able to line up better, and so there are more places where you could have those London dispersion forces.